Let's get started on 12.1, and this is just kind of a brief section introduction of three-dimensional coordinate system. Probably are familiar with to some level. So first, let's just do a quick review. When you have just a number line of real numbers, so you have the real numbers. So those are the reals. Symbol would be the R of the two lines like that. And that's really R1. That's how you'd indicate it. And that's considered one dimension or one-dimensional system, essentially. Then mostly what you've done up till now would be considered two-dimensional. So it's a two-dimensional system in a plane. Calc 1 and Calc 2 are mostly in the in the plane that's 2D. So this would be your XY. And essentially you have two real numbers, and that's two real number lines that cross. That's considered R2, a little superscript like that, and that's a two-dimensional or 2D coordinate system. So we want to get into 3D mostly. So when we do Calc 3, you're kind of doing Calc 1 and Calc 2 in some ways all over again, but you're doing it in 3 dimensions. So the chapters at first look a little disjoint. First we do vectors, then we get into differentiation. Well, then you get into vector valued functions. Then you get into differentiation or partial differentials. Then you get into integration. And then the last chapter, you kind of put it all together, which is called vector analysis. It's essentially introduction of vector analysis. So you are working in mostly 3D, but we can introduce higher dimensional concepts as well, which have now become very applicable in physics and all kinds of areas now. All right, so to draw on a paper or iPad, for what I'm using, a three-dimensional system, you do it in a certain way. So the vertical axis, like the y, that's usually your z-axis, and then what comes out, so that's z. Then usually this one that comes out like this is like coming out of the paper or the pad. That's your x-axis, and then you draw it kind of similarly like this along for your y. Doesn't really matter where you put it, like that, and that's your y-axis. So that is what we refer to as R3, or a three-dimensional coordinate system. So we can talk about, in 2D, what we have is an ordered pair. In 3 dimensions, we have an ordered triple. So we can talk about counting off like 1, 2, 3, and then 1, 2, 3, 4. So it would be coming out to here, put like a little X where it comes down. Then we might go up to say 1, 2, 3, 4, 5. So that would be a point in space up here. You draw in the dots like that to kind of indicate how it's going. So that would be the ordered triple, 3, 4, 5. I forgot you can also spruce this up a little bit by putting in dotted lines that kind of kind of make it look like it's going back into the paper like that. And this one would be the same dashes. That's the negative directions. Didn't draw that all too well, but you get the idea. So what we have then is an ordered triple, X, Y, and then Z. The origin, of course, is 0, 0, 0. So then let's talk about the planes. So the X, Y plane would be what? So in 2 dimensions, if I said I want to talk about the x-axis, what do I say? I say y is equal to 0. So this is kind of similar So for the xy plane, what I say then is z is equal to 0. And what is implied is x and y are anything arbitrary. And then we have the yz plane. We would then say x is equal to 0, and then similarly for yz, and then x, the z plane. We'd say y is equal to 0. This is where it's kind of tough to just go through this in this format of presenting, because it really doesn't, I can't really show you in real life what it looks like. I'm going to fix this. It's bugging me. So it kind of, one way to do this is to do a line, and then I erase this. You can do this with a straight edge too. You do like a line, you lined it up, and then you go in and erase it. Now it actually works pretty well with this pad, but it also works. There, see how that kind of dashes back like that, and you can kind of take your time on it if you want. So let's graph a few things. Let's look at a few different cases of what these graphs might look like in 3 dimensions. I'll show you a computer program to help graph and describe. So if I just were to say the graph of z equals 3, and then it's implied that x and y are anything real, then what does that create? That creates a plane up at z equals 3, or 3 units up, and it's a plane. Now sometimes those can be hard to draw. We'll do another one. X equals 4. Again, would be another plane where then the other 2 variables are arbitrary. So I'll show you what these are going to look like. I'll draw them first, best I can, and then I'll show you the computer stuff. So here's my coordinate system, x, y, and z. And so the first one is just up 3 units, and then you have a plane. So how do you draw a plane? Well, you kind of just have to just kind of go for it and draw it in there, kind of like this. And then there's a plane. And then you would say z is equal to 3. You're trying to indicate that it crosses maybe right there. And then you can maybe erase a little bit in the back here. Make sure that goes over the top like this, because it goes back behind it, right? Okay, so something like that maybe. And then x equal to 3 would be something out here, and it would be another plane that cuts through that. So you kind of draw it in like this. You kind of just do the best you can with a sketch. And then it's going like that, and it cuts right there. And so that's x equal to 3. Let me show you some graphs of that in the program. Now I have this one up already, and this is, so look at the function xyz is x plus y plus z equals 2. So this one you can see is, and of course it doesn't stop. This like kind of makes it stop in some kind of weird, 1, 2, 3, 4, 5, 6, almost like a 6 different sides. See what that looks like. So that's what the plane looks like, right? And then I can go in and on this thing to see the plane, we can go in and change it. So I can take that out, see if I have any built-in ones here already. These are all the ones I've done. So here's another plane, right, like that. See how that goes through right there? Okay, I don't need to do anything else in the other ones. You can kind of see how that's going to work. So that gives you an idea how you can do the planes, what they are. So this one is z is arbitrary. That's why it's lining up exactly. See that with the z-axis. Okay, so we don't really need to draw them very well. We just need to know they're there because we're going to find, for example, we'll find maybe the area right there, or if you could chop something off on the top, find the volume. So let me show you one more here, see if I have it. So you could have something like that, and then something like this, and then there's a volume you could talk about. So that's a cylinder. We're going to talk about cylinders today, or at some point. Okay, so this one, look at the red. It's x squared plus z squared equals 9. So that's a circle, right? But then your y is arbitrary. So y extends out both directions, either side. Okay, and that's what we refer to as a cylinder. Okay, and those are basic concept or general concept of a cylinder we will go over. Okay, let's look at some more examples. So next, let's take a look at this one. So this is, so sketch, what would x squared plus y squared equal to 4 look like? And then you don't write this necessarily, but it's implied that z is in the reals. So in 2 dimensions, so sometimes you draw these in 2 and 3 dimensions. So in 2 dimensions first, you have a circle, right? So you can draw a circle, and sometimes this works, sometimes it doesn't. Okay, looks like it worked okay. So you have a circle, and your radius is 2, so 2, negative 2. But then in 3 dimensions, if you're graphing this, what do you get? So let's draw it over here. So you get oops, I didn't mean to do that. Okay, so let's draw this and this. Okay, there's my axis again. So yeah, you're getting basically a circle, radius 2, and then it's going to extend all the way down. Oops, sorry. Like that. Okay, and you just make it look okay. No need to make it be perfect. Sometimes I can't help myself. I'm going to make it a little better. Okay, and it's not, just these are sketches. We do the best we can, but you do need to learn how to do these. X, Y, and Z. So that's what it would look like if you're asked to graph it. So it's a cylinder, what we consider as like a regular cylinder. And for some of you who's taken me before, I would always bring in that silver cylinder for my drinking water, and that's what this basically looks like, except it goes on forever. So now, what if I said, let's also restrict it to, so this would be another example. So same as above, and then I'll write that down. So x squared plus y squared equal to 4. And this one's kind of hard to, again, describe or show you, but without kind of being there. But think about it. What is this one going to do? So, and then y is equal to z. So you have this and that together, and what is that going to do? So try to sketch that. And I'll go ahead and show you. Basically what you do is you end up getting this diagonal like that. So it's on the cylinder, plus it's this line, or that plane that would cut through it. So just picture a plane cutting through that cylinder on that diagonal. So that's what the graph would be. Okay, then we have, I'll save the next one, so I'll just show you which one it's going to be. In 2.1, number 20. So we'll save this for problem set sections. This is number 20. And it basically says describe the graph. So we'll do that next. Okay, moving along. probably go ahead and leave some space here. So when I come back, I can go right to that. Let's look at the next thing is distance formula and spheres in 3D. So distance formula. And the equation of a sphere. So we're going to be building equations that describe all these different shapes in 3 dimensions. So let's let P1 be the point x1, y1, z1. Those are all the subscripts, right? And P2 be x2, y2, z2. And this is in 3, we say is 3 space or 3D. I'll use that interchangeably, or I'll say that interchangeably. So I'm not going to get into how you derive this, but basically it's very similar. Distance formula, distance between P1 and P2 is equal to, and there's, so you take the difference of each coordinate, and then you square it. So you're using basically Pythagorean theorem to describe it. So it's the square root of, may not need that much, but it's x2, excuse me, minus x1 squared plus y2 minus y1 squared. And of course, it doesn't matter the order. When you subtract them, you're squaring it anyway. Okay, so that's the distance formula. And you basically use that from any point to describe a sphere. So if you make one of these fixed and one of them arbitrary, then you get a fixed distance, say r, then you square both sides and you get the formula for a sphere. So say sphere of radius A centered at the origin is basically what we're saying then is, let's just say this is 0, 0, 0. And it's a center at the origin of radius, or I said radius A. And then so this is the distance from the point, from the arbitrary values. So then you get x squared plus y squared plus z squared is equal to a squared. Okay, so that's the center is 0, 0, 0. And then if it's centered at a point, we'll call it x naught, y naught, z naught, then it's x minus x naught squared plus y minus y naught squared plus z minus z naught squared equal to a squared. And that's centered at what we'll say is p naught, which is x naught, y naught, z naught. Okay, so that sphere, one way to draw these pictures is to try to do the, it doesn't always work for me, but you do the figure first. So you draw like a circle, and then you draw and try to draw the sphere. Sometimes this works, sometimes it doesn't. And then from there, you can draw in the coordinate system. So from there, you'll say, oh, the center is right here, and that's going to go up like that. And I kind of missed. It's okay. Like this, and like this. So we're going to start building all these different formulas, but that's what a sphere is, center at the origin, how you can draw it. Okay, a few more problems to do in there and go over for homework set, and then we'll go over 12.2. So that's actually rather short. Next is 12.2.